The projected demand for artificial intelligence computational power is reaching a point where it feels less like an engineering challenge and more like a physical crisis. By the year 2030, leading supercomputers are expected to require 2 million chips and 9 gigawatts of power. That is a staggering amount of energy, enough to power a small city. While current trends show hardware costs and energy consumption doubling every single year, a consensus is forming among experts that traditional digital processors are hitting a hard wall. We are facing a sustainability paradox where improved operational efficiency is completely overshadowed by the massive embodied carbon footprint of fabrication. This means that even if a chip uses less electricity while running, the process of making it creates so much pollution that the net gain is minimal. Here is the thing. Most people think the solution is just making faster graphics processing units or GPUs. But GPUs were designed for rendering images, not for the massive matrix multiplications required by modern machine learning. When you push them to their limit, they generate heat that requires massive cooling infrastructure, which adds even more energy consumption. This creates a feedback loop where the hardware becomes the bottleneck. To break this loop, we need to look at fundamentally different architectures. One of the most promising contenders is the development of electronic-photonic integrated circuits. Let me explain what that means in practical terms. Traditional chips rely on electrons moving through copper wires. This creates resistance and heat. Electronic-photonic integrated circuits, often abbreviated as EPICs, use light instead of electricity to transmit data. Imagine a highway where cars are replaced by beams of light. The traffic moves faster, there is no friction, and there is no heat generated by the movement itself. This allows for superior bandwidth and significantly lower energy consumption compared to traditional electronic GPUs. Some projections suggest these light-based architectures could deliver 100 times the speed improvements of current technology. This is the kind of leap that could finally meet the monumental demand without burning through the planet's resources. However, there is a catch that engineers need to understand immediately. While EPICs offer a path to reduced embodied carbon because they can utilize relaxed process nodes, there is a significant knowledge gap regarding their immediate scalability. We know how to mass-produce silicon chips today. We do not yet know how to mass-produce photonic chips at the same scale. The industry is currently growing rapidly with silicon-based supercomputers, but that growth is unsustainable. If we switch to EPICs too quickly, we might face a shortage of components. If we stay with silicon, we face an energy crisis. This creates a difficult transition period where the cost per token for AI services might actually spike before it drops. This brings us to the second major shift happening in the field. We are moving away from a centralized cloud model toward a distributed ecosystem. Instead of sending all data to a massive data center, specialized AI chips are being deployed at the edge. This means the computing happens closer to where the data is generated, like on a factory floor or inside a smart device. This shift requires new system strategies to optimize data, models, and hardware for efficiency. Techniques like model pruning and quantization are becoming essential. Pruning is like trimming a tree to help it grow stronger, removing unnecessary connections in the neural network. Quantization reduces the precision of the numbers the chip uses, trading a tiny bit of accuracy for a massive gain in speed and memory usage. Now consider the tools we use to build these chips. The design and verification of advanced chips are being revolutionized by AI-native electronic design automation tools. Electronic design automation is the software engineers use to lay out the physical design of a chip. Currently, classical methods are hitting a plateau because the complexity is too high for human logic alone. AI-native large circuit models aim to transcend this by unifying logic and physical layouts. Essentially, the software that designs the chip is itself powered by artificial intelligence, capable of handling the complexity of next-generation architectures that classical methods cannot manage. This is a parallel paradigm shift that might be just as important as the hardware itself. This creates a fierce competitive landscape. Major players like AMD are launching dedicated AI processors to challenge NVIDIA's dominance. A vast array of specialized integrated circuits and intellectual property are maturing to support diverse workloads. But for the engineer looking at cost per token and latency, the picture remains complex. Cost per token refers to the expense of processing a single unit of data, which is the key metric for profitability in AI services. Latency is the delay between a request and a response. Photonic chips promise lower latency, but the supply chain maturity is not there yet. Neuromorphic chips, which mimic the human brain structure, offer incredible efficiency for specific tasks but lack general-purpose flexibility. Ultimately, while hardware efficiency and design automation offer promising pathways, the industry currently lacks a unified strategy. We are trying to solve the physical limitations of fabrication, the energy costs of massive data centers, and the latency requirements of edge computing all at once. It is like trying to fix the engine, the fuel tank, and the steering wheel of a car simultaneously while it is driving at full speed. A holistic data model system triad is required at the edge to handle resource-constrained environments. We need a strategy that addresses the physical limitations of fabrication, the energy costs of massive data centers, and the latency requirements of edge computing. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.